All right. Hi. So this is going to be a bit different. I've never done this live. So it's going to be a Blackboard talk, and I'm going to try to write here, and it might go horribly wrong, but it might go right. So I'm not sure. So bear with me. All right. So remember that in the first thing we had this high-level overview, and now we have this second part where we drill down into one topic, and I try to give you more details on this. And we're going to do unsupervised learning, which you remember was the thing where we didn't know the labels. We just tried to reproduce the data somehow. And we're going to do something called principal component analysis, or the singular value decomposition and its families. And now, before I start, let me ask you a question. So here is the scenario. A friend of yours comes to you, and there is a new movie, say Oppenheimer, some movie. And you have seen it, they haven't seen it, right? And they want to know from you whether they should go and see it, whether they could like it, that movie. You don't want to describe the movie to the person, but you can ask them questions. So what would be the sort of questions you would ask to figure out whether that person could like that movie? Yes, very good. What kind of movies do you like? So movie problem would be, what kind, genre do you like? Will be another question. Any other ideas? Yes. Yeah, maybe general interests. Very good. Yeah. What other interests, maybe? Let's write this here. Other interests. But if you say you don't know, the genre is always a bit difficult thing, but say, that person has seen not only that movie you want to see, but also other movies. What other things could you ask them other than the genre?
Not for Oppenheimer, but if something can trigger a particular person, some particular event.
Yeah, triggering. Right. Other ideas? Director, directors. Yes.
If it's too long, or like.
Yeah, or that. So some other features that the movie has. Any other ideas? All right. I have one. What other movies did you like?
Maybe I can say that. Yeah, in principle, this is the last question, and I think because this is a friend of mine, not some very non well known human, then I think I should more or less understand what kind of movies did yeah.
Okay, I should know the person, the personality somehow,
Yes,
right?
But
something about the person, right? Yes. All right. I think that gives us a broad overview of the things. And it actually outlines two of the main techniques we have in supervised learning. If we ask the question, what other movies do we like? We make connections between the movies, right? So that leads us directly to a technique called clustering. where we try to find groups between movies and analyze distances between movies. We don't actually need to understand the genres. We just need to know how the movies relate to each other, right? And if we like some information about the genre, which kind of movie do you like? Which genre? What kind of a person are you? What are your other interests? And try to match that, sort of match some specific features between the movie and the person. So we distill both of them down to some intermediate space, right? The genre or the personality or the interests or the directors or that sort of thing. That thing is the second way we can understand unsupervised learning. And that leads us to low rank approximations or compression of the data. And that first thing, these low rank approximations, is the thing we're actually going to explore in this hour or so. Yes.
And what is rank? And what is high rank approximation? How we differ with low rank?
Hold on to that question for about 2 minutes. I'm going to explain to you exactly what that is now. And the explanation is the following. When we talk about the rank of a matrix, so we have a matrix. So let me see if that works. Oh, no, that doesn't work. I thought that, oh no. So I have this matrix, remember? And that matrix, for instance, collects that information. That was our design matrix, that matrix X, right? And now suppose our observations were here the persons. So each person is an observation, and each feature is a movie. And here we have that person likes that movie or that person dislikes the movie. Suppose we knew all that. Suppose we knew every single person what kind of movie he or she likes. Suppose we had that information, or at least for a subset. And now a low rank approximation would say, I'm going to decompose the matrix into the product of two matrices. A matrix product, that is. And remember what a matrix product does. It multiplies always row-wise. So it multiplies to get to this element, say. It would multiply this row by this column, for instance, right? To get to exactly that element. Now, still we have here the persons, and still we have here the movies, right? And now, lo and behold, we have this other dimension. This dimension that fits here and here. These are the two dimensions we multiply with each other. And these are now the genres. So in other words, what we are going to do is say, well, whether a person likes a movie is determined by whether a person likes a genre times whether the movie fits that genre. So that matrix X is decomposed into a matrix A times a matrix B. So in other words, the matrix, the person P and the movie M is then the sum of all genres. A person likes genre times B genre fits movie. That's the idea. Now, back to the question what we mean by low rank. this is, if you remember your linear algebra class, is a low rank matrix. So the rank of a matrix is the number of its independent rows and columns. When we have here, or in other words, it's this dimension here. The number of genres would be the rank. So if we need as many genres as we need movies, then this is a very bad idea, right? Because that would mean that there are no really good genres. Every movie is its own thing. But suppose we have a good way to define those genres. There are not that many genres. Then we can at least approximately decompose the matrix like this. So if we have 20 genres, we would have a rank 20 approximation to that matrix. So that's the basic idea. So, and that is unsupervised learning, because this thing is an approximation to our matrix. Remember, we called that X hat. And it depends on the parameters A and B. So we managed to approximately reconstruct the way whether a person likes a movie by a very natural decomposition, whether the person likes a genre times whether the genre fits a movie. Questions? Quite interesting, isn't it? It's a strange concept, and now you see, well, that's the structure we enforce. Remember, I said we have to plug in some structure, and that structure is fairly generic. We just said, well, there's redundancy in our data. We didn't actually say what kind of structure that is. We just said there is some redundancy. There exists some genres. But the natural question is, well, how do we figure these genres out? Suppose you're Netflix and you don't want to go through, I don't know how many Netflix movies are there, but probably a bazillion. You don't want to go through every single Netflix movie and characterize it as genres. And then you have every user figure out the huge questionnaire where they like this movie or this genre or this genre. And they say, oh, do you like, I don't know, film noir, French film noir films of the 40s? And they say, I don't know what that even is, you know? So there must be some better way to do this. Any idea how we could do this?
Okay, the easiest way that sometimes genres is defined by producers. Sometimes, yeah, it's predefined. Also, sometimes genres is determined by some, I don't know, critics, stuff like this. Yep. Sometimes it's hard to attribute the movie to some genre. Sometimes it's difficult because there are a lot of movies what are in some kinds experimental, or what contains the mixture of different genres and contains features of. And probably it should be the opinion of people, some opinion of people. So which
that's one version, yeah. Human domain specific knowledge. Any other ideas?
Maybe you just skim over the movie for looking for certain features. So, like, I don't know, maybe you can program something where you're looking if like there's a lot of laughing in the movie. I guess you can very easy in
sound processing. Very good. Yeah, that's also a good idea. Same, yes.
You look at other people and they see like if they all like the movie, maybe that's fits the same genre.
Yeah, that's also good. If we were to do this with machine learning, what we would do instead is, remember that we have here a matrix and some approximation to that matrix, right? So how did we learn how to match these two? How did we learn here? Well, what we did was we said, well, we have the movie, the matrix X, where we have a person and a movie. So we have person and movie. And we had this X hat person movie, our approximation. That depends on these parameters. Well, how about we simply match the two by minimizing the distance? So we figure out which values do we have to place here in this matrix such that this distance here is minimal. So, and if we don't have the full matrix available, then we have to ignore the items that are not there. But so it might be that there is a projector there that accounts for the items that we don't have. And that's it. But interestingly, what comes out of there is quite curious. Because suppose we can solve this. Then we don't actually plugged in any genres. We just said there is this structure. We didn't specify the genres. We didn't specify whether a user likes a genre. We didn't specify which movie fits that genre. We just had the matrix of some people liking that genre, imposing that low rank structure, and that gives us the genres quite naturally. So the genres are not determined by us as people. We don't go through the movies and say, does it fit these genres? But the genres are determined by the fact that we want to approximate that matrix well. And that is quite powerful. That means that is the thing that we say, all right, we know there is data, structure in that data, figure out a structure such that we can reproduce the data. That's the idea. Right. So, and that is the core of this, right? So in practice, that means that, for instance, if we have a materials database and we want to figure out feature or groups of this, we would, for instance, have a periodic table of elements. Remember, the rows would be the elements, the columns would be some properties. And then we would have some emergent features just by the fact that we require this table to have some, or we find some structure in that data. Right. Now that's the thing. Okay. Is that clear? Sort of the program. So there are packages that can do this, and we will figure out soon how to do this actually. All right. So that means that really the genres are learned. They are not predefined. And they are learned by requiring that we match the matrix. That's the only requirement we impose. Now, the downside is that we have to go back over the data afterwards and try to figure out what these genres mean. For example, so there is a thing that people did with personality tests. So most of them are crap, but there is one of them that is interestingly, that was determined by this kind of procedure. They looked at, their matrix was essentially all the participants and answers they gave on certain questions of a personality test. And they tried to figure out whether these answers could be determined by sort of personality traits, sort of genres of people, if you like, personality traits. And if then these questions would match the personality type. And so they ran a machine learning analysis very similar to that and found out that there were 5 traits that would predict most of the answers to that question. So you would classify a person after these 5 traits, and then that would predict more or less the answers to the personality test. The interesting thing is, if you do it like this, the model does not tell you what these traits mean. You have to go back and see, okay, this trait is more active, depends or is more active in these questions, so it's probably something like introversion, extroversion. But these were labels that the researcher attached post facto, ex post. They first looked at the classification and they say, okay, what could these genres mean? So it could, for instance, be that you're a very well-defined genre in your Netflix thing would be movies where, I don't know, Nicolas Cage does some escape thing and plays in the 1970s, and I don't know, Harrison Ford is not there or something, or I don't know. That could be a movie genre, but you would find that out after the fact, just by the fact that you would predict this matrix. All right, questions? All right, then let me tell you how to actually compute this. And how to compute this is by a technique called the singular value decomposition. And it's regrettably one of the things that you don't learn in your linear algebra class. And I'm very sad that we don't. So just by show of hands, who took linear algebra and learned about eigendecompositions and stuff like that? Probably everyone, right? Who remembers it? More or less. Okay, okay, good. Now then, let's do a quick reminder. Suppose you have a matrix X. And that matrix is square. And suppose also it's symmetric. Then that matrix has a spectral decomposition or the eigendecomposition. For instance, if it's a Hamiltonian, then it has an eigendecomposition. So it decomposes. Actually, to make this more clear, I'm going to call that matrix X transpose X, because then it's certainly symmetric, right? But that matrix can always be decomposed in a matrix V, which is just a rotation, then a diagonal matrix, which contains, if this is positive definite, it contains some elements, and then some rotation back. Now, or in other words, you have a set of eigenvectors that live like this, V1, V2, and so on. Then you have a diagonal matrix where you have some eigenvalues. And then we have a matrix where we just have these eigenvectors stacked like this. So that would be the reminder. So that would be, if you have the eigendecomposition of a symmetric positive definite matrix, then this is how it would look like. And so if you have a Hamiltonian, the values that you have in the middle would be the energies, and the vectors would be the rotations that you have to perform to get to these eigenstates. For instance, if you remember your quantum mechanics, you would have the eigenenergies, and then you have the eigenstates in some basis that you write down there. All right. Now, what you can do, however, is you can only do that with a symmetric matrix. It has to be square at least, right? But it turns out there is a generalization of this concept, and that is called the singular value decomposition. And what it does is it exists for any matrix X. And it decomposes that matrix into 3 parts again. There is a rotation, then a diagonal matrix, and then a rotation back. So you have here some vectors. Then you have some scalings. And then you have some other vectors that define your rotation. Okay. So that's what the singular value decomposition does. Now, observe that we had to relax one requirement of the eigen decomposition. So if you remember, if you have a quantum mechanical system, you can rotate into the eigenbasis, then multiply by some eigenvalue or do a time evolution, then rotate out of it with the same transformation. You undo it. You rotate in, and then you rotate back. If you have an arbitrary matrix, you can still do that, but you have to rotate back with a different transformation. So U and V are different objects. So that's the thing. And to do an example, let's think about, for instance, so we want to do an example and understand why X is U as V transpose. And let's do an example that, for instance, is this transformation here. Sorry, 1 0 1 1 1 0. So like this. So that thing doesn't have an eigen decomposition. And what it does is, if you start, for instance, with a square, okay, it leaves the x-axis unchanged, but the y-axis is so the new x-axis is just like this, but the y-axis looks like this. So it turns it, if you do x times this square, it just turns it into this sheared beast. And then what you can basically do to get from there to there is you apply this x. And now we want to figure out how to actually do this with these rotations. And now the statement would be that you first rotate it, then you scale the axis, and then you rotate it back. Let me see if I can manage. So you would first, if I remember correctly, I think you have to rotate it like this. So that would be the rotation. And then you basically scale this axis stronger than this axis to sort of shear it like this. So you just scale it in this direction stronger. And then you just rotate it back, but you rotate it with a different angle, a bit larger angle, and then it looks like this. So, I mean, if you open your Mathematica notebook and try it, it works. But practice, you do a scaling where you first rotate the thing, then you scale the thing, and then you rotate it back. So that's what generally you can do. So any transformation that you do can be done by a rotation, scaling, rotation back. Now, however, that's sort of the thing, right? So that means that this singular value decomposition is a way to decompose, to change this guy into a set of numbers, if you like. Now, what I would like to convince you now of is that this matrix here takes our movies and rotates it into the genres. this matrix here scales the genres by importance. And this matrix here rotates the genres into the people, or the people into the genres. And that's how this works. And to do that, I'm going to write this in a slightly different way. So remember that we have U times S times V transpose. So we're going to write X as the sum of a small k is 1 to capital K. So I'm going to just factor out each of these terms. SK times this UK times this VK transpose. Now that's just stating the system above, but we've separated out each of these S's into a separate term. Right. Now, the point is now that I can always choose, these S are always non-negative. So I can choose them so that S1 is greater equal to S2, is greater equal to S3, and so on. Right? This is always what I can do. Because they are ordered, so I can order them. They're non-negative numbers, so and they're always greater equal to 0. So then these S's are the importance of the genre, remember. And then we need one more statement that is quite nice, and I will not prove this to you. And that is that the norm of a matrix, 2 norm of a matrix, is its first or highest singular value. So the most important genre, the importance of the most important genre in a way, is the highest singular value, and that's the norm of a matrix. The norm of a matrix, remember, is the maximum amount it scales. That's exactly the importance of that thing. And now the punchline. The punchline is, suppose now, remember we want to make our low rank approximation. So we want to remove some of this information, right? That was the point. We want to have these genres and we don't want to take all of them. So how about for our approximated matrix, we just take the most important K prime. So we stopped at some earlier point. With this K prime being smaller than K. Right? Now that is a low rank approximation. So it's an approximation that is smaller. We don't use all the data. We use just a couple of vectors. So in this case, it would just mean cutting away some of that part, cutting away some of that part, and cutting away some of that part here. So observe that already that looks very close to this thing, right? And that is sort of the idea. So we stopped at some, so we cut some of that part away. Well, suppose we did that. And now we compute. Remember, that's the thing we want to minimize, the error we want to make by that approximation. Well, what is that? Any ideas? So I would be very impressed if you guessed that. But it's all here. In principle, you could figure it out.
But here we have only one rotation and one scaling. Yes.
No, you mean here in this bottom
Yes.
part? No, it's always, this is, I've ordered it in a different way, but it's always rotation with this V, then scaling, and then rotation back, right? It still has these 3 parts. I just separated them out. U is always the rotation into the genres, then S is the scaling, and V is the rotation back.
Okay, okay.
I'd be very impressed if you got this. Huh? Say again? You're on the right track. Yes. If we take, true, if we take all k, if we take k prime equal to k, we get the matrix back, then it would be 0. But S is a good thing, but it's not S1. Precisely, it's Sk plus 1, Sk prime plus 1. It's the first singular value we discard. Because that's exactly what comes out of this. We ordered them. So here's another way to understand the singular values. We remember that's the importance of the genres. So the error we are making by cutting away some of these genres is the importance of the first genre we didn't consider. Surely. And that also tells us how to actually assess the quality of our approximation. So you take our data matrix, the experimentalist up there, somebody, you run it through your NumPy SVD, you get your genres of your data, and then you say, well, what about I take 3 genres of my data? And I said, how good approximation is that? Well, I just look at the 4th genre and check its importance. That's it. It tells me how important that is. Isn't that cool? And that is the key, really. This technique is so powerful that it is underlying a field of what's called tensor networks, low-rank approximation. It's become a hugely successful way to think about physics data. And generalizations of this concept are found in what's called autoencoders, which underlie now large language models. All these classification ideas of pictures, of images, all of them rely on the fact that you rotate into some genres, weight the genres, and rotate back into the space. Yes. Oh, there was a question now? And that's pretty cool. And it just is at your fingertips. You just do an SVD. Yes. What? Sorry?
How do you decide when to put K prime?
Well, it's the question with which error you're satisfied with. Because you know what the error approximation error is. So you might be satisfied with a 1% approximation error. And then you cut away all the genres that have less than a 1% influence on your, so Sk prime plus 1 divided by S1 would be the relative importance, right? And you would just cut them away if they're less than 1%, for instance. Yes.
I'm just saying, like, yes, then you can decide what the precision you want. But I guess if you choose a lower K, then the system will be faster.
It is then
the entire calculations will be faster.
Yes, that's true.
So
the calculations are faster, so it's easier to. I mean, it depends how large your matrix is. So if your matrix is, so it scales. Computing this low-rank approximation scales as the number of features times the number of observations times the number of features you want to keep. So that's the scaling. So if you want to keep many features, then it's a problem. But I mean, your typical if your matrix is not too large, you don't care. You just compute the whole thing and look at the data. The other thing I want to say here is it's very pertinent in a sense. If you take the bias variance trade-off still bites you. If you take singular values, genres that are unimportant, right? You get lots and lots of, you don't actually learn or put differently, if you take all the genres possible, you can reproduce the full matrix, but you haven't actually learned anything about the matrix. You just rephrase the matrix in a different way. If you take a single or 2 or 3 genres, you have actually learned something. You have taken the most important data and tried to abstract from it. Now that's again the bias variance trade-off rephrased. Very nice. Yes.
Higher dimension matrix, a lower dimension matrix from a higher dimension matrix, because X is a greater dimension matrix, right? And X hat is a smaller dimension.
Very, very good. They actually are the same size because these vectors are the same size. So if you, it's just, so put differently, if you multiply these three matrices together, they just make a matrix of the same number of components. It builds it from smaller matrices, from smaller constituents. That's the difference. So otherwise it would, you're absolutely right. Otherwise this would not make sense. Very good point. So it just says there's less internal structure in a way. It's more like an Emmental cheese. It's the same size, but it has more holes in it, right? All right. All right, I want to demonstrate this for you with an example. And I hope I can do this. So this is actually an example from my lecture. And we are going to, I want to just show you how these kinds of techniques work. So what are we going to look at is the Ising model. So just by show of hands, who has heard of the Ising model before? Everybody. Very good. So you have a grid of spin one half objects, or spins, classical spins that can point up and down. That's probably more correct. And you arrange them in a grid, some grid, and then they interact with each other, and then you have this nice phase transition. Now, let's suppose we go through this like a typewriter. Then we can understand an observation as one of these configurations that happen in our model at some point. And we just, the features or the observables would just be all the spins, right? And we have to order them somehow to get a matrix, otherwise it gets complicated with tensors and stuff. So suppose we just strung them up like this. Now, let me just move that to the side. We would, so I will give you the solution that's maybe not good for the next year's exercise, because I will have to change it. But in practice, here's the magic. We take that matrix, which has, again, maybe I'll draw it like this. We would have now all the spins, you know, there would be like up, down, 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 up. And this would be one configuration. And here would be the next configuration. So this would be configuration number 1. This would be number 2, and so on. And this would just be the spins, and I've just strung them up in order, right? And that's our matrix X. And now I take one of these temperatures and a couple of configurations there, and just do an SVD. And it's just literally this line. And now what I can do, what I can do is plot these singular values. And here are they. So I've plotted them on a log scale. K is the singular value index. You see they are sorted. So what would you conclude when you see that? Okay, well, what do we observe here first? Is there anything that catches your eye on this plot? Non-linear, true. Observe there is this thing up there. You see that blue, single blue point. The first singular value is very large, and all the others are much, much smaller. So what does that tell us? Remember, what does it tell us if only one singular value really matters?
Some linear single genre. Oh.
Single rank?
Single rank. Yes.
Yeah.
The rank is low. Yeah.
Okay. Any other ideas? You had one or no? Okay. Single rank, yes. Or a single genre. Remember, a single genre is important. What would that genre be? Any ideas for the Ising model? Yeah. What say would that be, for instance, for the Ising model? Up, down, up, down, up, down. Yeah, for instance, for the antiferromagnetic or for the ferromagnetic model would be just the genre would be, is the magnetization would be the genre. Is it magnetized up or down? That's it. Because we are 1.75 is below the critical temperature, so the system magnetizes. So the only thing that really matters in our analysis is which direction does it magnetize? It's the only information that is, because we know all the spins are the same there. So it just means we have one field. We only need one information point per configuration. Is it magnetized up or down? That's the genre. Simple genre, not very interesting, but that's the genre, right? So the whole matrix can be described just by repeating a single spin. And which spin to repeat is noted in that varies from observation to observation, depending on the magnetization. Observe, I didn't put this in there. I just required that to represent that. And in fact, if we now, okay, yes. So what I've plotted to you here is, again, this matrix here. So X, the left panel, is the matrix. And so all the rows are the different configurations that your Ising model could be. And the columns, so each one of these lines is one configuration. And you see that mostly they're horizontal lines, which just means that all the spins in the configuration are mostly the same. You see a bit of dots. And now the model tells us, well, this is our model, which is just an alignment here, right? All the spins are the same, and they vary by configuration. And the difference you see on the right-hand side, and see, is very slight. And it would be consistent with the second feature. Now, you see that's the cool thing. And now after the fact, we can go back and say, oh, obviously that's the magnetization. And that's the power of these unsupervised techniques, that I didn't put anything in. It tells me the structure, and then I can go back after the fact to analyze it. Isn't that cool? Questions?
Can you a little bit explain again the density matrix, like what the structure of it is previously? Then, like, yeah.
This matrix, what its structure is?
No, just X.
X.
Like initially, how you have defined X? Like
X, yes. So X I defined is a set of spins. So I have 1,000 different configurations that the Ising model typically takes at a certain temperature, right? So, and each of these configurations is a single line. But it actually is a field of spins, right? So what I did was basically, I took all the spins and assigned a value of spin up to black and the value of spin down to white, or vice versa, it doesn't matter. And then I took all the rows of this pattern and just strung them up like this. And then I get this matrix, right? So a single configuration is a single line, a single row in that matrix. And it is a configuration is a single sort of, the approximation is a single line in that second matrix. So that's why there are some, in the real data, there are some always flipped. There's always like processes, entropic processes that flip some of these spins, right? Yes. Yes, precisely. 1600 spins, 40 by 40, just a 40 by 40. Right.
Yeah, if we will look at a different model, let's say where we have 3 spin configurations, how would the singular value decomposition look? Like the plot will have 2 points much higher than the rest?
Well, it's interesting, right? So if there is just, it's still all the same, but it's 3 possible values, then it would be still a single feature that determines everything, right? That doesn't depend on how many values that feature can take, as long as it's a scalar, right? But if it's 2-dimensional, for instance, if it's a direction, say, in a XY plane or in on the Bloch sphere, then you would have 2 features that are important. You're absolutely right. It's a very good point. And now the interesting thing comes when I now did the same thing for a higher temperature. So the blue curve is the one you've seen before. And the orange curve is now the curve for a higher temperature, and in particular above the critical temperature, which for this model is about 2.3 or so. Now, what would we say, what we conclude from that orange curve? You think about our genre analogy.
You need to keep.
Correct. You need much more parameters. You need more genres. There is more going on. But that's clear, because remember what temperature is. Temperature introduces randomness in our data. So randomness is barely compressible, which means we need more data. We need more data. There's intrinsically more stuff going on. And in particular, once we're above the critical temperature, the spins randomize. So they form domains, but they're mostly random. So that means we need the information, we need more information to understand all of these domains. And that's exactly what the singular value decomposition already tells you. And in particular, if we now do a rank 10 approximation, so this left side would be the same data, but for higher temperature. And you see, it almost looks already like a TV static. Oh God, you're all too young for that, aren't you? All right, imagine old movies where you still have that TV static. It looks like, okay, it looks like noise anyway. But you see there is a little bit is going on, right? It's not exactly, there seems to be a bit of structure there still, right? And in fact, there is. And if we do a rank 10 approximation, a rank 1 approximation would be pretty bad. You see that structure emerge here. That's X1 is actually wrong, it's X10. So you see that structure emerge. It tries to capture some of that features. And what remains then on the other side is mostly noise. So that already looks pretty much unstructured noise. So it allows us now to separate again the information from the noise. And that's what this allows. The genres are now less well defined, and typically they will be in your data. But they already, you need now intrinsically more genres because there's more information with it. Now you could go back and understand, what do these genres mean? And we can understand maybe the first genre still corresponds to something like overall magnetization. Second genre might correspond to something like cluster size. But that's something we can figure out after the fact. We don't need to bias ourselves at first by plugging that in. Any questions? think I steamrolled over you, probably. But
I'm sorry, cannot relate to what you said previously. Just can you repeat again what are matrices U and V in this case?
so I can actually show you. So let's take the case of high temperature, right? Low temperature, where a rank 1 matrix is sufficient, right? And let me show you what U is. You see, so this matrix U, remember, is the rotation from the rows, which are the observations, into that genre space, right? And you see it's mostly the same number, except it changes sign. You see it's plus 0.3, minus 0.3, plus 0.3, 0.03, minus 0.03. So actually, probably if I multiply, because this has to be normed, so I think I have to probably multiply it with the number of observations. Yes. So you think, see, the norming is sort of because you want these things to be normalized because they're eigenvectors and things. But if you multiply this by a factor, you get +1 or -1. So this matrix U tells you the spin configuration. So the feature, remember, that, or the genre we determined it would be just the magnetization. And that would be that matrix U. The matrix U would tell you for each of our observations, is it polarized up or polarized down? So that might be the first thing. Then S is the importance of that feature. So the importance would be some number. The important thing is not so much the importance of that feature, that depends on the scaling, how you scale your data, but in relation to, for instance, the second feature. And you see it's almost 2 orders of magnitude. So in other words, that first feature is already a very good predictor. And by ignoring the second feature, you make an error of maybe 1% or so, you know? So that was the second part. And then let's take the third part, which was our V, right? Transpose actually. Let's transpose that. And we do it times 600. Right. Me. Okay, what you have to take my word for it is that all these values are basically -1. Right? Essentially. All of the values are -1. And remember what the V matrix told us. It told us how the features are, the genres relate to the movies, the features are observables. And we said what matters is essentially the total magnetization, because we have a polarized state. So this thing tells us, well, if you have a state that has a feature of +1, the way you get the configuration is basically just by repeating that thing all over, because it just multiplies it by a constant vector. So you get always the same value, up, 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 or down, 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 down. And that's a polarized state. So again, it tells you how the observables then relate back to the singular values. It takes a little time to get used to it, but that's really the connection is then these genres, right? So the genre of your magnetic material would be how it's magnetized, and then the observations would relate to which way, sort of a factor, up or down. And the other one would just tell you, oh, it means magnetized means all the spins are the same. That would be the 3 factors. Very good point. Yes. Right, I think it's past. We should probably stop. I'm pretty much done. If there's questions, I'm happy to stay.
You are going to show rank 10.
This will be rank 10. This was rank 10 for the high temperature.
Okay, I thought it is rank. Okay, yes.
Yeah, and that was rank 1 for the low temperature. We can try. Let's try. I think we should have 2.25 somewhere, but I think it's this one. Yeah, that's actually quite cool. What you see is the behavior is qualitatively between the two. So it's really, I mean, you see the onset that you still have one, but the behavior changes. It doesn't have this sharp drop, but it doesn't have this slope. It has something in between. I mean, we're not directly, but 2.25, we're slightly below the critical temperature. And so what you find then is that you get a regime that is in between the two. I hope I can plot this. That actually there is still, you need a lot of singular values, but there is not as much structure as in the high temperature, in the low temperature phase, but not quite as little structure as in the high temperature phase. So it's exactly in between the two. Yeah, it's very also it's interesting. It doesn't capture. It only has you allude to a very important point. We're doing linear algebra, so the only transformation we're allowed to figure out our genres are linear transformations. But of course, in this critical regime, we have more complicated transformations potentially, and that we don't figure out. The SVD has no idea of to. And then there are more advanced ideas like autoencoders, which allow these two rotations into the genre to be more complicated. For instance, you could use a neural network for that. Yeah, there are more interesting ideas. Unfortunately, there are what's called tensor networks, which try to take the spatial structure into account. And there are very, very interesting ideas there in what's called the multilinear algebra. And there is a very rich field here.
So maybe just like the same direction, because like, as you said, like, or as George said, basically it's linear algebra, but is there also ways that, for example, that you can look for second order correlations?
Yes. So there is a method called, so staying with a similar framework, right? Where we say we have a transformation of both the observation and the feature space into a small space of genres. So I call it genres. There's a technical term for it. We call it a latent space. So a space that underlies that data. And there are more complicated transformations to allow you to go to that latent space. So for instance, you could say you have a nonlinear transformation and you still optimize for the same cost function that you reproduced. It's more complicated because nonlinear optimization is complicated, but in principle, it's possible. Or you could, there are more interesting ideas, but I mean, in principle, the variational autoencoder idea is that. So if you do image classifications, the chances are that what you are using is something like this, but instead of two matrices, U and V, you have two neural networks, U and V. And that's really cool, actually. One of the most powerful techniques in existence, I think. Yes.
So, I mean, I understand the concept that the Ising model is pretty, this academic example. Can you give a example in which singular value decomposition has been used in a, I don't know, maybe a recent paper or recent research?
So there is an idea. So yes. So one of the ideas that we used it, for instance, for are what called inverse problems. So what's an inverse problem? Suppose you have a spectrum from some lamp or some frequency spectrum that your detector gives you, right? What you find is that you don't find the actual spectrum, but your spectrum is broadened by temperature. It's mirrored. You have Doppler broadening, essentially. Natural, you have other broadenings too, but the thing you cannot really get away from is Doppler broadening. So you have in other words, you have let's do it with thing. Then you have say a spectrum, and there's a bunch of peaks that are in some absorption lines. What you actually observe is something like this. Right? Probably. Now it turns out there is a matrix that gets you from here to there, or a kernel. So some transformation that gets you from there to there, right? And it turns out what you can do is, it's actually very hard to get from here to here, because there's always many choices you can make how to fit that data. So it's actually not at all easy to extract these sharp lines from this, because some information is lost. And what you do is, well, let's try our luck with an SVD then. And what you find when you do this is, you see that there are, on this side, you get certain functions. So these vectors are then, these genres are then like moments of your spectrum a little bit. And then it tells you how to relate the blurry spectrum to the noisy spectrum, essentially. By saying, I project this noisy spectrum on those features, and then I scale them by 1 over the singular value, and then I project it back. So in other words, it allows you to undo this transformation, x to the -1, by saying, well, x to the -1 is just, well, this is v, it just trades places. This is just 1 over s, and that's just U transpose, right? So it tells you to say, well, let's map this first to this. So it tells you the blurred spectrum is the blurred spectrum is, you take your real spectrum, you rotate it into the genres, you scale them, and then you unrotate it to the blurred features. And here it tells you just to do the reverse. Rotate it to the thing, then scale them by importance, by inverse importance, and then return to the scale them back to the unblurred features. Now here's the kicker. The problem is the bias variance trade-off kicks in, because these guys get very small. S gets very small as you lose information. The exact position of these peaks at some points doesn't matter so much to these guys, which means these singular values get very small, which means the inverse of the singular values get very large. So if you have any noise in your data, you will amplify it. And that's the old thing. So, you know, when you watch your CSI Miami, where they get basically a picture of there, you get 10 pixel, and then they have a magical button, enhance, and suddenly you can see the reflection in the retina of the knife of the killer. Then, well, you could possibly do that, but the problem is that you would end up with only noise, right? You cannot enhance what isn't there. And the singular value decomposition tells you exactly how much needs to be there to make sense. And we use this technique to basically work with spectra, with electronic spectra. We know how much information remains, and we store only that information that remains. And it's an idea called the IR basis. And it's a quite nice idea that if you do many-body calculations, then it's a simple but nice idea where this actually works. Yes.
But I guess you could work around this problem if you have some more restrictions to the problem. If, for example,
Yes.
in a quantum gas microscope, when you know the distance between particles.
Yes, that's actually a very important point. This is unbiased in the sense it's the best spectrum you can get, or most likely, one should say most likely spectrum we get without further information. If you plug in further information, you of course can beat this thing. It's again the thing, if you remember your bias variance trade-off, there was one error that says add knowledge how to reduce this. This would be exactly that. Very good point.
Okay, so if there is no more questions, then we should thank the lecturer.